So, we started with discussing propagators and propagators in the context of quantum mechanics, and then we introduced Green's function and how the propagator is related to the Green's function, and then we have started talking about second quantization. So, which is basically the beginning or start of the course, and so it is a good time to talk about the references which you should be referring to. So, the references are, some of the references are, I will probably include more references as we go along. Some of them are Quantum Many Particle System by Nagele and Orland. It is a 11th books publication and it has an Indian edition. The Quantum Theory of Many Particle System, which is a classic by Fetter and Wolichka. It is a McGraw-Hill publication. A Many Particle Physics by Gerald D. Mahan. It is a Springer publication and quite a popular book. Then it is a Condensed Matter Field Theory by Altland and Simmons, which is a Cambridge University Press publication. And then for other things such as superconductivity, we will mostly refer to Tinkham, which is Dover publications. And in addition to that, we will refer to some other scientific articles other than books or maybe research papers, which we shall cite from time to time. So, with this, let us go back to the issue of second quantization that we have been discussing, and let us now convince ourselves that the one that the symmetrization of the quantum many particle state, which was encoded in a complicated factor and which had to be summed over, as we have seen in previous lecture in equation 1 to be precise, that can be taken care of by using states which are formed by creation and annihilation operators, and this symmetrization is actually taken care by the commutation relations of these operators, the creation and the annihilation operators. So, let us take a simple example, and where I can write down a quantum state as A1 dagger, A2 dagger and acting on 0. So, this if we change 1 and 2, it would go to A2 dagger, A1 dagger, and we have said earlier that for bosons it does not make a difference, that is there is no sign that comes in front of this the second term on your right. However, for fermions we get a negative sign. So, this is negative sign comes for fermions, and just that this negative sign can also be obtained if we consider the anti-commutation relations of this two operators, which is written as this, which is equal to 0, and this immediately means that the A1 dagger, A2 dagger plus A2 dagger, A1 dagger equal to 0, A1 dagger equal to 0, and the consequence is that if I change the position, I will get a minus sign, as you can see from here. So, this minus sign that you are getting is actually taking care of the swapping of particle or transposition of the coordinates of the particle, and hence we should pick up a minus sign. So, I think by now it is clear that how the tremendous work of symmetrizing 10 to the power 23 number of particles, which is Avogadro number of particles in any system, how that huge symmetrization requirement can be taken care of by writing the many particle state in terms of the creation and the annihilation operators. So, now we shall go ahead and talk about the how to write down single particle operators and maybe two particle operators, or rather many particle operators in this second quantized form in terms of the creation and the annihilation operators. So, we now know how to write down a state psi in terms of A dagger, etc. Okay. The next thing is talking about one body operators. So, this is the next thing. So, representation of one body operators. And there are many examples of one body operators, and they would in principle be written as this, and then there is a sum, and then there is a n. So, we always put a cap when we particularly want to denote operators. And so, this single particle operator, this sub 1 or the subscript 1 actually talk about that it is a one body operator. So, it is a summation over such operators for n particles, where n is any number, in principle can go from 0 to infinity. And so, I am writing down a one body operator as a sum of the one body operators of a system, where n refers to the number of particles or any other quantum number that is relevant for the problem. And similarly, we can have an example for this is, so one example is the kinetic energy operator. So, this kinetic energy operator talks about, or this quantifies the, rather it gives you the observable for the kinetic energy for a given system, and we can write this as T, which is equal to P n square over 2 m, where m is the mass of the particle. Okay. So, this is the total energy of a system, which consists of the individual energies of the particles, which are represented like this. Then we can have one body potential which is written like V of, so this will be like V n x n and sum over n. Here P is also an operator which can have a form which is minus I h cross del, which is the differential operator. And similarly, we can also have the spin operator so S, which is a sum over n and S n and so on. So, there are many examples of that. So, the question is that how to write one body operators in terms of the creation and the annihilation operators. So, we will write them as A dagger. So, that is the question that we are going to handle now. So, now let us look at this problem and let us define occupation number operator which is n lambda, which is equal to A lambda dagger A lambda. So, this operator operates on a particle state, say lambda j, which, so this is the operator and it is acting on a many particle state and gives me n lambda j and then returns me back the state n lambda 1, n lambda 2, etcetera. So, it basically counts the number of particles in the state lambda. So, I will write this because this is important, counts the number of particles in the particular state lambda. In this case, we have taken lambda j as one of the representative states of this many particle system. So, if we have such a definition for an occupation number operator, then we can write down any one particle operator, say let us call it as O1 as we have written earlier, which considered is assumed to be diagonal in lambda basis. What it means is that a O1 operator equal to O lambda I, and there is a so this is equal to a lambda I and a lambda I. So, this is the meaning that it is diagonal in the lambda basis, and where my O lambda I equal to a lambda I O and a lambda I. Well, lambda is a particular state as we have shown there. So, now with this nomenclature, let us calculate the matrix elements of O1. So, the matrix elements of O1 is written as n lambda 1 prime, n lambda 2 prime, there is no prime here. So, these are just the state, and then I have this and n lambda 1, n lambda 2. I am sure that you know that the matrix elements of an operator is computed in this fashion. So, you squeeze it between two states which are from the Hilbert space. So, n lambda prime and n lambda form the Hilbert space of the problem, and then you have this is equal to a O lambda I, n lambda I, and now I will have this n lambda 1 prime, n lambda 2 prime, and so on, and then n lambda 1, n lambda 2, and so on. So, that is my matrix elements of the one body operator, which I am trying to write in terms of the creation and the annihilation operators. So, this equality actually holds for any set of states. So, one can write down for O1 the second quantized representation as in the following. So, your O1 is this, and so this is a lambda equal to 0 to infinity, and then there is a O lambda n lambda, which is equal to a lambda equal to 0 to infinity, and a lambda O 1 lambda and a lambda dagger a lambda. So, because we have said, if you look at equation, let us call this as equation 1 and let us call this as equation 2, this as equation 3. So, if you look at equation 1, then my operator O1 is represented as the matrix element of that operator in the lambda basis, as you can see, and then there is a lambda dagger a lambda, which is nothing but the occupation number n lambda that is written here, and let us call this as equation 4. So, the interpretation is straightforward that a one body operator engages a single particle state at a time, and then the other states are simply just the spectators, and in a diagonal representation one simply counts the number of particles in a state lambda, which is given by n lambda, and multiplies it corresponding to the eigenvalue of the one particle operator between its eigenstates lambda. Okay. And now one can generalize it to a non-diagonal basis and can write this as this operator now in terms of a general basis where the operator is not diagonal in the lambda basis, you can still write it as so. This is the representation of a general representation of a one body operator in terms of the creation and the annihilation operators. So, this is called as the second quantization or the second quantized notation for a one body operator. Let us take an example. Let us call this as equation 5, and now let us write down for a spin operator. So, we are giving examples, and this I will write this SI operator and write the matrix elements of the SI operators between two states, which is given by alpha and alpha prime. So, this is basically nothing but the components of the spin. In ordinary quantum mechanics, you have studied spin. Even in non-relativistic mechanics, quantum mechanics, we add spin by hand, whereas in the Dirac theory, the relativistic theory, the spin comes naturally. So, for a spin half object, the spin operator is a 2 by 2 operator, and for spin 1 it is a 3 by 3 operator. For spin half, it has a special name called as a Pauli spin matrices. So, the components of the spin so this is equal to half of sigma I and alpha prime. There is a H cross here in place of 1, but which we have taken it as this H cross has been taken as 1 here. So, this is the representation of of a spin operator, and this spin operator is going to be now written in terms of the creation and the annihilation operators. So, just before that, just for completeness, let me introduce the Pauli spin matrices as so. I have a sigma x, which is 0 1 1 0, a sigma y corresponding to the special direction y, and there is a sigma z which is 1 0 0 minus 1. The important thing about them is that the trace of all these is 0 identically. Sigma x and sigma y are off diagonal matrices, whereas sigma z is diagonal. In fact, because it is diagonal, it is chosen as a preferred variable, or the z axis is chosen as a preferred direction in most of the problems that we do in physics. So, what I mean by trace equal to 0 is the sum of the diagonal elements is equal to 0. You can see that, check that here. So, now I can write down a spin operator as simply equal to A lambda alpha prime dagger S alpha alpha prime A lambda alpha, where lambda actually denotes some other quantum number, and here is basically the space variable. So, lambda denotes a space variable such as x and y. So, this is the representation of the spin operator in the second quantized notation, where we have written as so this is the matrix element S alpha alpha prime is the matrix element as we have shown in above, and then A lambda dagger and A lambda alpha etcetera, they are creation and annihilation operators. Let us do another example which is of use to us. Let us do it for the kinetic energy, and so we can also do it for kinetic energy and a one body potential. And this will specifically write in the real space basis. So, a Hamiltonian consisting of the kinetic energy and a one body potential is written as d d r A dagger r, and there is a p square over 2 m plus a v of r, and so these r's are, so these are vectors and written as this. And so, this is the Hamiltonian which consists of a kinetic energy and a one body potential. The kinetic energy is given by p square over 2 m, and and this v of r is just a potential at a given site r, and p is written as minus I h cross del, where del is an operator, it is a differential operator that acts on space. And similarly, a local density operator can be written as rho of r equal to A dagger r A r. And in the above example, you see that we have written it because r is a space variable in continuum. In the continuum representation, we have written it as an integral instead of a sum, and this integral is taken in d dimension. So, it is a dr. So, whereas in 3 dimension we would write it as d cube r, or you can write it as a volume integral dv, the same thing. So, now having done the one body operator, let us talk about the two body operator, representation of two body. Okay. So, these two body operators are used to denote pairwise interaction between particles. So, whenever two particles are interacting with each other by a potential which could be of any form, which could have form such as 1 over r, which is called as a Coulomb interaction, or for that matter any other form of interaction, then this is called as a we need a two body operator to represent that. And in principle, we can do it for any n body operator. However, interaction potentials beyond a two body term is not something that we encounter in physical problems, or we see in physical problems, and that is why we shall restrict ourselves to a two body operator, and that would be good enough for writing a Hamiltonian for a system, for a many particle system. So, let us see how we can do that, and for doing that we note that in classical problems there is no sort of, it can be written straightforwardly because of the distinguishability of particles. However, in quantum many body theory or quantum mechanics, the indistinguishability makes it somewhat harder to write. So, let us take a symmetric potential, symmetric two body potential. By symmetric, what I mean is that V R N R M, where M, N and M, they refer to two sides maybe, and this is equal to V R M R N. So, the potential or the interaction potential that one body exerts, one body at N exerts on another body at M is the same as the interaction potential that is exerted by the body at M and on N. So, this is we have now, so we will write this as, so we will take a real space representation and these are vectors, and we have, see, we are going from, initially we have started with a coordinate representation or a position representation for a many particle state, and then we had gone to a occupation number or the number operator formalism, and now in this particular case we are coming back to the real space representations, but ultimately you will have to write down a Hamiltonian in the same basis, or rather if you have to solve it, you have to do it on the same basis. However, here we prefer to do it in the real space basis, and we write it as this V R N R M. We can put vectors here as well, and this is equal R 1 R 2, and there is a R N. So, this is where we had to restrict the sum to all n values which are less than m. Otherwise, we would be double counting, because V R N R M is same as V R M R N. If we do not have this constraint, then we would be double counting this interaction term. However, it is difficult to keep track of these indices, one being less than the other. So, it is easier to introduce a factor of half and write this as n equal to or n not equal to m, and it goes like this. So, this is my representation of the two body operator written. So, as it acts on a basis state that is given by this. Now, we can take a two body interaction term in vacuum as this is equal to a half, and again written as a d d r and a d d r prime, and the a dagger r prime and v r r prime a r prime a r. So, that is the form of the potential or a two body potential. This, see that it contains two creation operators and two annihilation operators. As opposed to the one body term which contained one creation operator and one annihilation operator. Now, this can be written as in a general sense and in any basis, just like what we have done it for the one body operator. We will write a two body operator as so this is written in terms of scattering events. I will describe how, and this is equal to lambda lambda prime and a mu mu prime, and then this is O mu mu prime lambda lambda prime, and there is a mu dagger a mu prime dagger a lambda prime. So, this is the matrix element of the two body operator between two states mu mu prime and lambda lambda prime. So, what happens is that a state from lambda and so one particle from a state lambda and another particle from the state lambda prime, they scatter onto two states mu and mu prime. So, these are annihilating, lambda and lambda prime are annihilating, and they are getting created in the state as in the mu and mu prime states. So, this is the matrix element of the two body operator in the mu mu prime and lambda lambda prime states, and these are the corresponding creation and annihilation operators. So, it could happen that mu equal to mu prime or mu equal to lambda and mu prime equal to lambda prime, all that can happen, but in principle this can be denoted as a scattering event . So, I will draw that scattering event. A pictorial representation of that scattering event can be like this, and there is some interaction there, and it could be going like this. So, there is a lambda coming. So, a particle from a state lambda is coming, a particle from a state lambda prime is coming, and they are getting created in mu and mu prime. It could also happen that the lambda goes to mu prime and lambda prime goes to mu, but that is equally a possibility for this scattering problems. So, this is a simplest vertex that we can think of, or there could be more complicated vertices which take away some energy momentum, which we will learn when we are going to do Feynman diagrams. So, in those cases we will see that we have a vertex having a structure, and that structure will depend upon the specifics of the interaction term. That could actually depend upon the interaction term can actually depend upon. So, here the interaction amplitude of the interaction term is constant. Here it could depend upon r, or it could depend upon spin, or it could depend upon momentum, and then we have them getting recreated here. So, we have a lambda and a lambda prime, and they are getting recreated as mu and a mu prime. So, these are the basic representations of the two particle operators. So, now I will summarize that we now know how to write down a many particle state in terms of creation and annihilation operators, and we also know how to write down one particle operator and two particle operator in the second quantized notation. So, once again I reiterate that the name second quantization is justified as we have been able to write down both the state and the operators that represent observables in the quantized notation, or what we call a second quantization, where both of these quantities are represented as operators, the creation and the annihilation operators. And to end the discussion, the proper symmetry requirements of fermions or bosons are encoded in the anti-commutation and the commutation relations respectively in these problems. So, we shall wind up this discussion with an example which is for the two body spin-spin interaction. That is, we are going to talk about a Hamiltonian where the only interaction that is there is via two spins, and they would be interacting in a particular way. And this is in a spin only model, and that we would be writing it as a half factor to avoid double counting, and then there is a d d r prime, and I have alpha alpha prime beta beta prime, and there is a amplitude which is given by, that is the amplitude of the spin spin interaction, which is given by j r r prime, and there is a s alpha beta dotted with s alpha prime beta prime. And now I will write the, so r and a alpha prime dagger r prime, and I also have a beta prime r prime and a beta r. So, this is a typical example of a two body interaction for a spinner system where two spins are interacting via potential which is given like this. We will get into more examples later.